Yesterday we have started cryptography, right? Group codes, actually. It is using group theory concept. You might have studied this using linear algebra concept. Both are dependent on each other, actually, right? Okay. So there are two things. So why we encode a message? What do you mean by encoding a message? You are adding something or doing something in that message in such a way that the message, when it is sent, okay, either it will not be hacked, or while at the end, if you are receiving, even if there is any mistake, you will be able to identify what is the mistake and get back your original message. So at least even if when something happens to the message also, you'll be able to identify where could be the mistake, and you should be able to track the what mistake and correct it. So for that purpose only we always encode a message, right? So encoder is a device which transforms the incoming messages in such a way that presence of noise, that's what they are saying technically, but I said something differently. That's all. Presence of noise in the transformed message is detectable, right? Decoder. So I think whenever there is encoder, whenever you are encoding a message, the receiver should be able to decode the message. What do you mean by decoding a message? You have to retrieve back the original message. Something is being added or something you have changed the message. So only the receiver should know what should be done so that he could get back the original message. So decoder is that thing which does that work, right? So this is the actually hierarchy. There will be a transmitter. 1 minute. Okay. So there is a transmitter. Okay. From the transmitter, encoder encodes the message. Then it is moving through the proper channel. So in between, noise can attack it or it can join it. Then when it receives the receiver, before that it is getting decoded, receiver will receive the proper message, right? See, the message need not be numbers, the message need not be alphabets. The way we send the message also, the way we encode, we don't know that we don't have a proper, I cannot say only I can encode a message only by this technique. We have lot of procedures, lots of techniques are there. These are all whatever we are learning are very preliminary things, just an introduction. So nowadays we are encoding it through polynomials. We are finding a polynomial such that it cannot be decoded. So nobody can hack that particular message. In that way, we are finding polynomials for encoding the messages, right? They are called permutation polynomials. It will permute the messages in such a way that you cannot identify it. So whenever you permute 4 letters, somewhat you can guess. But if there is a lengthy message, and if you are permuting something out of it, will it be possible to identify what is the permutation that has been done and what is the original message? No, not at all possible, right? So what is a group code first? So the procedure what we are going to use here is group code technique. You have learned cosets, right? You know groups, you know cosets. Cosets come out of what? Subgroups. Groups are there, subgroups are there. So using subgroups, we can construct the cosets. So actually cosets, what they do? They partition the entire group, right? Coset technique only we are going to use it here, right? So only zeros and ones we are going to use. So why zeros and ones? Whenever there are only two terms, which is more easier, yeah? See, you have only two things, either 0 or 1, either false or true. So if there is a mistake, I say if there is a mistake in the 5th position, what will you do? If that position value is 0, I'm saying that value is wrong. So what will be the correct value?
1.
1. So correcting and identifying the mistake is easy whenever only two possible values. So that way always we go for binary. What is this actually Z2? Remember what is Z2? Or simply Z2. What is Z2? Group theory concept only you are using. What is Z2? Just now we have seen here. 2-3 hours back or maybe before Cat 1. What is Z2?
0 and 1.
The set of the numbers or the device, the reminders that we obtain whenever any positive integer is divided by 2. So what are the possible reminders? 0 and 1. So Z2 has 0 and 1. So you know very well Z2 is a group under addition modulo 2. Clear? Z2 is a group under addition modulo 2. You accept this?
Yes, ma'am.
Yes, it is a group under addition modulo 2. So instead of B, we are going to consider B power n. See, for example, here I have given you B square. So B is 0, 1. B is nothing but Z2n. Here they are using B. Okay, if B is 0, 1, your B square is, it is nothing but a direct product of B and B. So direct product means what you take? 0, 0 you take, 0, 1 you take. So 0, 0, 0, 1. Then 1, 0, 1, 1. All the 4 elements. These are the 4 elements. This is actually nothing but Z2 cross Z2. Direct product of two sets. Okay. So you obtain 4 elements. I'm going to say that even these 4 elements obtained in this way, it is also a group under the same addition modulo 2. Okay. So here you have to take care. Addition modulo 2 is the operation. Take care. So I'm forming the KLA table. Adding 0, 0 and 0, 0. How do you add? 0, 0, 0, 0. If you add 0 plus 0, 0, 0. So same 0. 0, 0 with any number will get the same thing here. But after all, you are not adding anything. So we'll get back all the same. First row and first column, very easy. Go to the second row. 0, 1, 0, 1. If you add, how do you get? Here I have added. See, 0, 1, 0, 1. If you add, what happens? 1 plus 1 is what? Under addition modulo 2. 1 plus 1 is?
0.
0.
0.
Then 0 plus 0 is 0. So 0, 1 plus 0, 1 is nothing but 0, 0. Right? Okay, now 0, 1 plus 1, 0. If you add, what happens? See, how do you obtain this element? If you add this and this. 0, 1, 1, 0. If you add 1 plus 0 is 1. Addition modulo 2. 0 plus 1 is also 1. So 1, 1. So same way I have completed the KLA table. Right? Now we are in the process of saying that it is a group. Can you say it is closed? All the elements in the KLA table are what? Elements of
B
the
square.
group B square itself. So it is closed. So that is okay. Okay, associative property holds good because it is addition modulo 2. Then what about identity? What is the identity element? What is the identity here?
0, 0.
0, 0. Okay, can you say the inverse of each and every element? Inverse of 0, 1?
0, 1.
0, 1. Inverse of 1, 0?
1, 0.
1, 0. Inverse of 1, 1?
1, 1.
1, 1, nah? Same 1, 1.
Yes, ma'am. 1, 1.
Okay, what type of group is this then? It is a group. Something more can you add? A square, B square, C square, all are E. Okay, that is A plus A 0, 1 addition modulo 2, 0, 1 is 0, 0. 1, 0 addition modulo 2, 1, 0 is 0, 0. 1, 1 addition modulo 2, 1, 1 is 0, 0. So by observing all these things, one more I'll do. 0, 1 addition modulo 2, 1, 0, you are getting 1, 1. Correct? The third element you are getting. Similarly, 1, 0, 1, 1, if you add, what will you get? 1, 0, you'll get the third element. So when you add two elements, you are getting the third element. If you add the one element with itself, you are getting back 0, 0. So what is this type of group?
Kleins 4 group.
Klein's form. Because it's a group of order 4. It's a Klein's form. Very good, clear. So B square is a group. So B cube means how many elements will be there? Can you say what are all the elements in B cube? Just I'll write here.
Excuse me, ma'am.
Yes, Vita, tell me.
How are we doing the % 2 operator like modulo 2?
How are we doing?
The modulo 2 operator, how are we doing?
Should I repeat that?
Yes, ma'am.
Just very simple, yeah. I'm adding 0, 1 and 1, 1. Term wise I have to add. 1 plus 1 is what? 2. So under addition modulo 2, 2 will be treated as?
0.
0. Okay, then 0 plus 1 if you add it is 1. So under addition modulo 2 is again 1. So
Okay,
0, 1 plus 1, 1 is 1, 0. Clear?
Yes, got it.
Okay. Then 1, 1, 1, 1 if you add 1, 1, 1, 1. Same way, yeah. 1 plus 1 is 2. Under addition modulo 2 it is 0. 1 plus 1 is 2. Under addition modulo it is 0. So 1, 1 plus 1, 1 is, it is actually 0, 0. Point is clear?
Yes, ma'am.
Yes, yes. So same way I'm saying that B cube is a group. So B cube will have what type of elements? Very simple, yeah. When you form the truth table, what are all elements will come when you have what? When you take 3 variables, all those elements will come in B cube. Can you say now? 0, 0, 0, 0, 0, 1, 0, 1, 0,
100.
1, 0, 0, 1, 0, 1, 1, 1, 0,
110.
1, 1, 1. Clear, huh?
Yes, ma'am.
Something I left out, one element is missing. 1, 2, 3, 4, 5, 6, 7, all 8 elements I have written. So again, B cube is a group under addition modulo 2. So in general, B power n is a group under addition modulo 2. Concept clear? Hello? Hello, Bache, can you hear me? Can you understand?
Yes, ma'am.
Okay.
Yes, ma'am.
Sure. Okay. See, please read the first definition. If B is equal to 0, 1, then B power n is equal to, this is simply, no comma is not needed. You can write like this, x1, x2, etc., xn. How I write 0, 0, 0? The same way, x1, x2, etc. x1, x2, etc., xn will be nothing but either 0 or 1. So n elements just written together, all. It is a group under the binary operation. Addition modulo 2. Binary operation of binary operation addition modulo 2. So B power n addition modulo 2. Here also that's a mistake. It is addition modulo 2 is a group code. It is abelian always. Why it is abelian? Very simple. The operation addition is always
Addition.
right. Okay. See. So now we have got certain elements, right? These are the elements, these are the messages, the group codes, whatever we have, right? These are all the messages. Every element or every, see, suppose if you have a 3-letter word, everything will be converting into group codes. That conversion we are not going to see. You have a set of group codes like this, but I'm not going to send that as such. I'm going to add something called parity check entries at the end of each of the code. Suppose BQ means I had 8 codes. At the end of each, I'll add parity check entries, which is going to help us later. That one way I'm encoding it by adding some parity check entries, right? So the codes obtained by introducing additional digits called parity digits to the digits in the original message are called Hamming codes. Suppose from B cube, I have a number like this, 0, 0, 1. But I'm adding 2 parity check entries. 1, 1 I'm adding. Now it has become 5 entry data. It is an element of B power 5 now. I'm sending it now. I added 2 elements and sending it now. These 2 last entries, 1, 1, that is called the parity check. They are called parity check entries. And after adding it, originally it is the original code. And after adding it is called Hamming code. Okay. If the original message is a binary string of length m, So here original message is a binary string of length 3. Then the Hamming encoded message is of string length n. Here it is of length 5. So always this 5 will be greater than this 3. That's what they are given. So something needs to be added at the end. First m digits represents the information, actual information, and the remaining n minus m are used for detection and correction of the errors. Right? Okay. Very important. There are two things here. Either you can have even parity check or odd parity check. Right? So if you introduce a digit in the last position, so after introducing, if you have even number of ones, then you can call that as even parity check. After introducing something, if you have odd number of ones, then that is called odd parity check. See, for example, these are all the given digits. They are the elements of what here? These are all the elements of? No, what? They are the huh?
PQ.
PQ. What I am doing, I am adding some entries. After adding, can you say how many ones are here? 0. Here, 2. Here, 2. 2. 2. 2. 2. 4. So how many ones are there? It have even number of ones. So after adding something at the end, actually it is called an even parity check entry you have added. Okay, so if I want to make, you have to add ones in such a way that here it should become odd parity check. How can you add? 0, 0, 0 is there. I need odd number of ones. So you can add 1, 1. Here you didn't add anything. So if you have 0 number of ones, that is also treated as even. Always 0 also counts along with what? Even. Then 0, 0, 1 is there. If you add 0, it will have even number of ones. But here you added 1 so that even number of ones are there. Okay. What here you have to do? 0, 1, 0. Odd number of ones I need. So what should I do?
0 1 0 0.
0, 1, 0. Only 0 should be added. Here already 2 ones are there, but I need odd number of ones. So one more 1 you add. One entry I have to add here. Either I have to add 0 or 1. So take care by adding something. I need odd number of ones. So if already odd number of ones are there, add 0. If already even number of ones are there, add 1. Okay, 1, 0, 0. What do you have to add? I should add something at the end, either 0 or 1. One, 0, 0. How many ones are there already? Odd number of ones are there. So what will happen if you add a 1? It will become even parity check, but I need an odd parity check. So what you have to add?
0.
0. Similarly here, 1, 0, 1. Nama 1, 0, 1.
1, ma'am.
1. Here 1, 1, 0. 1.
1.
3 ones will come. Already odd number of ones are here, so add 0. So this is called odd parity check entries. Single odd parity check entries, and these are all called the single even parity check entries or even parity check words. Okay. These are some basic definitions. It's very easy. Group code is very easy. The number of ones in the binary string is called the weight of X. See, for example, can you see how many ones are here? 4 ones. So weight of this particular string is 4. And it is denoted by mod of X. Okay, if X and Y represent two binary strings, the number of positions in the string for which Xi is not equal to Yj is called the Hamming distance. See, for example, I consider two strings. Okay, first position, are they same? No.
No.
Second position, are they same? So don't count it, they are same. Third position, they are different. Here 0, here 1. Here also differs. So how many digits differ here in both the strings? 3 digits values differ. Second digit, they are one and the same. So how many such differences are there? That much number of that differences is called that count of the difference is called the Hamming distance. So what is the Hamming distance between these two things? Suppose this is your x and this is your y. Hamming distance of x comma y is 3. Okay, 100. One more example I'll give you. X is equal to 1, 1, 1, 0, 1, 1. And y is 0, 0, 1, 1, 0, 1. Can you find the Hamming distance between x and y?
4, ma'am.
Remember? 4, ah? Okay, first position they differ, second position they differ, third position same, fourth position they differ. Okay, fifth position they differ. So 4, Hamming distance is 4. Okay, you got it, right. Go to the third point. The minimum distance of a code is the minimum of the Hamming distances between all pairs of encoded words in that code. Suppose, see, you have 3 words here, X, Y, Z. So I'm finding the Hamming distance between what? X, Y first, Y, Z, then X, Z. So you can see which is the minimum most value here? 1. Hamming distance between X and Y is minimum most, and that is called the minimum distance of a code. Don't go further deep into this. Very important thing. I told you, suppose you have an entry like this. This is an element of B power 4. You can add parity check entries at the end, right? That parity check entries can be added manually. Either you can add or you can follow a procedure. You can have some matrix, which suppose you take all the B power 4 entries, you follow some regularity. Take a matrix. With the help of that matrix, add 3 entries at the end. Right? So such type of matrix is called a generator matrix, which is going to add parity check entries at the end. That matrix is called a generator matrix. The same thing you might have studied in your linear algebra, right? You'll be using a matrix to what? Encode the message. Here also you are going to use a matrix. Matrix plays a lot of role here, right? Because it transforms anything. It's a very basic example of linear transformation. So matrix plays a very important role. So same way here also you are going to use a matrix. That matrix is called generator matrix. See, for example, I want to encode a function. I'm taking an element of B cube and I'm going to convert that to an element of B power 6. That means I'm going to add 3 parity check entries at the end. Right? So B cube, how many entries will be there? 2 cube, 8 entries will be there. So for each of the 8 entries in B cube, I'm going to add 3 entries at the last. Okay, so you'll get 8 entries of B power 6. Okay, how to achieve that? That's what you have a matrix. So what is the format of that matrix is IMA. It's very important. I'll take one example and explain. You will understand why IMA. Suppose I want to define a function. This is called the encoding function here. B cube to B power 5. Okay. Can you see? It is I3. This is matrix A. Can you see? It is IM A. Okay, IM is M by M unit matrix, unity matrix, that is identity matrix. And A is M cross N minus M. If this is M here, 3, N is 5 minus 3, 2. So M cross N minus, that is 3 cross 2 matrix, A matrix. Right? I'll tell you how we are going to do this and you'll understand why this is happening.
Can you explain that last part? Not understand.
Not able to see the screen, huh?
And the last part I did not understand. The B3, I mean, how M is 3 and N is 2.
I'll repeat. Don't worry. See, my aim is I'm going to take an element of B cube. So you know what are all the elements of B cube, right? Okay. All these elements, I'm going to add 2 entries at the end. So for that, I'm defining a matrix. The matrix will be, this is called M. And this is called N. They use some symbol, we'll also follow that. B power M to B power N. So in that case, your generator matrix will look something like this. It should be IM slash A. So what is this IM? I3, M is 3 here, slash A. The dimension of A should be M into N minus N. That is M rows and N minus columns should be there. So M rows means 3 rows and 2 columns. So that is your A matrix. So for example, I am taking identity matrix. It is not going to change. Always it will remain. For example, I am taking a matrix like this. Can you understand this is a 3 row 2 column matrix? Hello? Hello?
Ma'am, A is Avish, ma'am.
A is the matrix. See, actually, this is a block matrix. Blocking means what? Augmenting and something. Can you see here? This is one matrix. This is one matrix. Writing them together. That matrix is called G matrix. G matrix is a 3 by 5 matrix actually. Okay. So 1 minute here, you will understand one operation I'll do. See, for example, I'll take this element. Okay. So I'm going to encode this word. E of 0, 1, 0. It is nothing but this into this matrix.
Ma'am, like we understood how we got the 3 by 2, that other part, but then like this 1, 0, 1, 1 and 0, 1, we can assume it randomly.
Randomly. The way you want to add the entries, that way you have to decide your A. Because the first 3 columns of your generator matrix is not going to disturb anything. 1 minute. Just 1 minute I'll tell you. Multiply this, what you get? Please tell me. How do you multiply? 0, 1, 0 into 1, 0, 0. If you multiply, 0. 0, 1, 0 into 0, 1, 0, you'll get 1. 0, 1, 0 into 0, 0, 1, you get 0. 0, 1, 0 into 1, 1, 0. 0, 1, 0 into 1, 1, 0. That means what? 0 into 1 plus 1 into 1 plus 0 into 0. So answer is 0 into 1, 0 plus 1 into 1, 1 plus 0 into 0. So finally 0 plus 1 plus 0, 1. Now 0, 1, 0 into this column. Hey, this is just like a 1 by 3 matrix and this is a 3 by 5 matrix. Now say next step. It is also 1. Okay, what I have done here, I have taken 0, 1, 0. Okay, I have added 2 entries at the end. First 3 entries are not disturbed because I want to add only 3 entries. So that's why I have taken care that the first 3 columns of the matrix are nothing but the columns of the identity matrix. Only if they are the columns of the identity matrix, these 3 entries will remain the same. It is not going to same. After all, you are going to add something at the end. You are not supposed to change anything. The first 3 letters should not be changed while you are encoding. For that purpose only, first 3 columns are identity matrix. Got it? Hello?
Yes, ma'am.
Yes.
Yes, ma'am.
So even can you find this? You multiply and tell me E of 1, 1, 1. You do it. Carefully multiply and say
Ma'am, for A we can take any values like
Anything,
any order, ma'am.
anything. Yes, sure, I understand. Anything. It's up to you what you want to weigh. The way you want to encode, you can add. Maybe more things later they will add. Many things will be there. This is the basic. Multiply and tell me.
One, 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 two, two,
1, 1, 1.
two, two.
Right. What is 2 under addition module?
Oh, 0.
Both 0, va? 0, 0. Okay. 1, 1, 1, 0, 0. So here also you observe these 3 entries will be fixed. Okay. That's why here first 3 columns are identity. Now you go back to the definition, you will understand. When m by n belong to z plus positive integer, m less than n, this is called the encoding function. How you encode, how do you achieve? How do you take an element of b power m to b power n? By multiplying an element of b power m with a matrix. What is that matrix called? Generator matrix. How is that matrix looking like? Im what augmented with a, that you have to do. So this matrix is called generator because it generates parity entries. Or this. Okay, take down this question. We'll do one question. Find the code words generated by the matrix when encoding function is b square to b power 5. So you got it. B square, see, can you see here? This is what? I2. And this is your A. Clear?
Yes, ma'am.
So they'll be more specific. They'll give you a generator matrix because they want to generate something, generate some parity check entries. So they will give a generator matrix. See, in linear algebra, for every matrix you had an inverse to get back the original. So same way here, for every generator matrix you have something called parity check matrix, which will be helping us to find whether the entries that we received are correct or not. Okay, we'll do this question. 1 0 0 1 1 1 0 0 1 1. Okay, 1 minute. Okay, tell me the matrix here. Z is equal to 1 0 0 1 1 1 0 0 1 1 1 0 0 1. So E is from B square to B power 5. B square elements are 0 0 0 1 1 0 1 1. I need to encode. So first I'll encode one element of B square, that is 0 0. So E of 0 0 is nothing but 0 0 into that matrix. First 2 entries you need not do, you directly write 0 0. It will come automatically. You start multiplying from here. Since you are multiplying by 0 0, everything will be 0 0. No matter. Then E of 0 1. What happened? Okay, 0 1 into can you multiply? I'm sure.
Zero one zero one one.
0 1 0 1 for fifth entry
1.
1. So can you find everything like this? 1 0 then 1 1 all please find.
10110.
10110. Okay. Then
11101.
11101. Okay. Correct. So how many elements will be there in B power 5 actually? Actually, how many elements? Huh?
2 power 5.
2 power 5. 2 power 5 is 32. So we are defining a function. See, 0, 0 is going to 0, 0, 0, 0, 0. 0, 1 is going to 0, 1, 0, 1, 1. 1, 0 going to 1, 0, 1, 1, 0. 1, 1 is going to 1, 0, 1. But many more elements are there. This function is not on to but 1 to 1. Right? Out of 32 elements, only 4 elements have the pre-image. So all these 4 elements of the domain are mapped onto 4 elements of B power 5. That means we are adding 3 elements at the end so that it becomes an element of B power 5. So this problem is over. That's all. Simple thing, just to understand. Okay. There is one more thing called, I told you, parity check matrix. Just like a generator matrix generates the parity check entries, right? Parity check matrix is a matrix which is going to help. That is, it will help us to check whether the receiver, whatever he is receiving, whether it is correct or not, right? Or if there is a problem, it will say whether in which position the problem is. Suppose you come to know that all B square entries have been added with 3 more entries. So you are receiving 4 entries. Out of those 4 entries, sometimes you may not receive all 4 entries correctly. So using this parity check matrix, what you can do is you can check whether the 4 entries, whatever each and every entry you can take and check whether it is correct or not. If it is not correct, at least you can find out where is the mistake, which position the mistake is. But the thing is, you can identify only a mistake if there is only one mistake. If there is more than one mistake, then something more you have to do. There is only one mistake, it is easy to find out. If there is more than one mistake, it's not that much easy. Right? So, but we are going to concentrate only things with only one error. If there are more than one error, then you will conclude that it cannot be detected. You cannot decode it uniquely. That is the way you are going to conclude. Don't worry, I'll teach you. Don't get confused. So how is this parity check matrix? What is the way it is being defined? See, this is the parity check matrix. See here. Whenever your G is IM/A, your parity check entries is just transpose this matrix and write IN minus M. Here IM means here IN minus M. This way you have to augment it. So whenever you know G, you can write H. And whenever you know H, you can write G. So what is H? Parity check matrix. If your G is IM/A, your H is A transpose I N minus M. Augmenting in a different way. Just remember this. Very important. This is the point. See, please listen. Suppose you have added parity check entries and you have sent the message. Okay, you have sent the message. You are receiving the message, right? After receiving the message, you want to check whether whatever message we have received, is it correct or not. So for that, I'm going to take the parity check matrix now. See, for example, if R is a received word, okay, 1 by n matrix. What I do is I multiply, that is I find what is H into R transpose. If H into R transpose is 0 column, that is completely full of zeros, then I can conclude that there is no error. Okay, whatever the sender has sent, the same thing the receiver also has received. No error in the middle. Nothing has happened. There is no error in the message. Okay. Suppose H dot R transpose is equal to ith column of H. Then I can say that there is a mistake in the ith position of the word received. Ith position, if it is 1, you have to correct it as 0. If it is 0, you have to correct it as 1. So that even there is a way of what? Detecting the error and also correcting. Okay. Suppose if your H transpose, H dot R transpose, neither case 1 nor case 2. That means what? It is not appearing as any of the column. Then your error cannot be detected. That means there is no one error. There is more than one error. So that's what the theorem says. This theorem and all we are not going to apply, so don't worry. A code can be corrected. A code can correct a set of at most k errors if and only if the minimum distance between any two code words is at least 2k plus 1. Don't go much deep into this. I'm not going to use this. Okay, find the code word generated by the encoding function with respect to the parity check matrix. Okay, here actually they should have given this way: A transpose I n minus m. It should not be given this way. They should write like this. I'm sorry. This is the correct way of writing. I'll change this. It should be cut like this and it should be brought here sideways. Can you understand? The block is here like this. It should be brought this way. Now you can understand. This is A transpose and this is what? I n minus m. So parity check matrix is given. They have asked us to find the code words generated by the generated matrix. Take this question, we'll do it now. I think we have time, enough time. What is the time?
25.
Cherima, okay. From the way you are saying itself, I can understand all are very, very tired.